Good morning. Okay, so I hope everybody had a great reading week. So the only announcement I have is with regard to the quiz. So please don't forget, quiz 4 has been posted on Learn, and the deadline will be this Thursday, 11:30 p.m. if I'm not mistaken. Okay, so just to recap, before the reading week, we were talking about uniprocessor scheduling. We talked about basic scheduling policies like first come, first serve, round robin, shortest task first. Then we talked about strict policy scheduling, multi-level queuing, and then the last that we talked about was how we can achieve fairness with lottery scheduling. So if you remember, the last thing we said was that lottery scheduling is fair on average, but in short windows, because everything is random, you could get to see the high variance of this random process. And with high variance, you probably in short windows don't satisfy fairness constraints. Now, let's see how we can address that. The next policy that we're going to talk about is called stride scheduling, from the same author of the lottery scheduling. So the same authors who proposed lottery scheduling, they studied it, and to address its shortcomings, they provided stride scheduling. So stride scheduling tries to address fairness without introducing randomness. So we want a deterministic policy of some sort. So when we take away randomness, we take away the variance that we had. So how does it work? So in stride scheduling, you define a stride for each thread, and the stride that each thread has is basically a big number. So the algorithm that I'm going to describe will be very similar to lottery scheduling. So we're going to have tickets. So for a stride, we just give a very big number divided by by the number of tickets that each thread has. So ni is the number of tickets that thread I has, or task I, or job I, whatever unit of scheduling you have. And then we just divide a very big number by everybody's tickets. So the larger your tickets are, the share of your tickets are, the lower and the smaller your stride becomes, because it's in the denominator, the number of tickets that you have. So here's an example. Let's say that big number W is 10,000, and let's say we have 3 threads, A, B, and C, and then let's say A has 100 tickets, B has 50 tickets, and C has 250 tickets. So C is the high priority task. It has more tickets. A is medium priority with 100, and then B is the lowest priority with 50 tickets. So the stride of A, B, and C become 100, 240. So the higher the number of tokens or tickets, the lower your stride becomes. Now, how do we use these strides? Well, we're going to divide time to time quanta, like round robin, and we're going to maintain a pass for each thread. So this is a counter per thread. Now, how do we update pass? Well, every time that the scheduler has to make a decision on who has to be scheduled, the scheduler picks the lowest pass at that time, and then gives the scheduler to that process. Once this happens, we add the stride of that thread to its pass. So the pass increases over time for all threads, and it increases every time a thread gets to use the CPU. How much does it increase? By the stride of that thread. So what happens with this scheduling is that if you have low stride, you can see that you will get more CPU time, because every time you get the CPU, your pass is going to be increased by a little bit because your stride is small. And if you have a big stride, if you have your stride is a large number, then the one time that you get the CPU, your pass is going to be increased by a lot. And then you will have to wait for other threads for their pass to come close to yours and surpass yours, so that you get scheduled next. So as you can see, if you have a bigger stride, you will get the CPU less than others. Yeah, I'm not going to go to details of this, but then you can prove with this scheduling that the time each thread gets on CPU, if you have long-running threads, is proportional to the number of tickets that they have. So in this example, for example, the A and B, if we look at the time they got on the CPU, we'll see that A will get twice as much as B gets, because A has twice as many tickets as B. And if we compare C to B, we'll see that C will get 5 times more than B gets. And that is apparent looking at their stride, because C's stride is 5 times smaller than B's. So when B gets one a stride added to its pass, C has to get 5 times to get its pass be equal to B's pass. Okay, now let's take the stride scheduling, let's build on top of this, and this becomes max-min fairness. So let me actually make that connection even more apparent. Here we're doing some sort of max-min, if you can see it. So what we're doing is we look at the minimum pass and we give CPU to that minimum pass. And by doing that, we want the pass to be increased. So it's kind of like maximizing the minimum pass. So every time we find the minimum pass, we give it the CPU, and by doing that, we add something to that pass, so we increase that minimum. So overall, what we're doing is we're just doing some sort of max-min on the pass, right? Now, the same idea, we're going to actually modify this max-min fairness to get it to where it is right now in Linux scheduler. So now let's assume that we want to do this max-min instead of on the pass. We want to do it on CPU time. So let's say we put aside the tickets. Let's say everybody is the same. Everybody has the same weight, right? If everybody has the same weight, then stride scheduling is basically becomes this max-min fairness that I'm describing here, because every time we want to find out who has gotten less time on CPU, and then we give it the CPU to the minimum guy. And if there are ties, we randomly break those ties. The same tie breaking rules actually apply to stride, because at the beginning everybody has the same pass. So whenever you have same pass, you break ties randomly. The same here. Now, if you do that, you can see that after n, so if you have n runnable threads in your system, right, each one of them gets 1/n of CPU time. Because every time you give CPU to one of them, you will find that the other ones now have less time. So you will start giving it to the others until everybody is the same. Then you go back to, it kind of becomes like a round robin. So basically what we want to do is, if you implement this scheduling at any given time, let's say time t, everybody gets t divided by n. Very similar to round robin. Now, depending on the length of the time quantum, this could have the same pitfalls and shortcomings than round robin has, and specifically it might do a lot of context switching, right? Because if you want to really implement exactly max-min fairness, you have to, schedule one instruction of one thread, and then after one instruction, then everybody else now has less time. So you have to go execute another instruction from another thread, and then another instruction from another thread, and that becomes really impractical to exactly implement max-min fairness. That's why instead of doing instruction per instruction, we just do time quantum one time quantum at a time. So we give one time quantum to this thread, and then we switch to another thread, and then switch to another thread. Now, depending on how large or how long this time quantum, the length of the time quantum is, you might end up context switching a lot. So yes, so here is the relaxed version where we do with time quanta. At each time quanta, we look at the thread that has the minimum accumulated time on the CPU. We pick that, we let it run for that time quanta, for that time quantum. Again, we look who's minimum. Again, this T2 is the minimum. We give it another shot. And then T3 becomes the minimum, and then we give T3 one time quantum on the CPU. So far, this max-min fairness assumes that everybody has the same weight. So first of all, before actually going there, do you notice any problem here? Well, the problem is this T1 has really poor response time. Let's say that this T1 was a game application or a video streaming application. It has to wait for T2 and T3 to get to its accumulated time on the CPU so that it can proceed, and that's basically really bad. So as the number of threads increases, it kind of becomes like round robin. You have to wait for everybody else until it's your turn. Now, can we fix this? Sort of. One fix that you could do is to dynamically change the time quantum, the length of time quantum. So you can define a target latency. You could say, I want every application to get to use the CPU at most every n units of time. So you say every 100 millisecond, for example, I want every single application in my system to at least run one time. So if that's the case, so if you can define that target latency, then you can define the time quantum, the length of time quantum, to be that number divided by the number of threads that you have in your ready queue. So if your target latency is 100 milliseconds and you have 10 tasks in your ready queue, then if you set time quantum to be 10 milliseconds, then at every 100 milliseconds, each task gets to run at least once. Very simple math. So basically, we dynamically now set the time quantum to be this target latency divided by the number of tasks in our system. And here is an example where we have, let's say the target latency is 20 milliseconds, and we have 4 threads in the ready queue. Then we can set the time quantum length to be 5 milliseconds. Now, this is not that rosy, everything right now. The reason is this n could be really large. So what happens, let's say, if you have this target latency of 20 milliseconds, but then you have 200 threads in your system? In that case, the length of your time quantum becomes 0.1 millisecond. Now, this should sound alarms in your mind. Why? Because this is very close to the context switching overhead. So the context switching overhead, if you remember, was very close to this number. And now your time quantum is very close to your overhead. And that's pretty bad. Because as you remember, we talked about this, that you want the context switching overhead to be about 1% of your time quantum. So in essence, although this works for lower number of n's, but it might not work for all systems when this number, the number of active threads in your system increases. So how can we fix that? We can actually define a minimum granularity in our system. It's kind of like we say the minimum time quantum length is this number that we're giving you. And it doesn't matter how many tasks there are in the system. So as long as this formula gives you a number higher than this minimum, use that number. But the moment that this time quantum becomes lower than minimum, you shouldn't go lower than minimum. You should stay with the minimum. So this is one fix we did to basically make our system more responsive. So that's kind of like changing the time quantum. And if you really have equal weights between all your threads, and let's say all your threads are always available, then this is basically round robin with dynamic time quantum length. Now, to make it a little bit more interesting, to have now priorities, to add priorities to this. So let's say now I don't have all my threads the same priority. Some of them have more priority, some of them have less priority. Can I add that notion to maximum fairness? And the answer is yes. You can actually add weights, very, very similar to the notion of tickets that we had. The moment you can add weights to this maximum fairness, and the idea is, okay, instead of looking at cumulative time on the CPU, you divide that by the weight of each thread. So it's very similar, actually, exactly the same notion that we had with stride scheduling. So now we're going to do time quantum per thread defined instead of having a global time quantum. So time quantum per thread for each thread becomes the, sorry, I apologize. So the time quantum is globally defined, the target latency divided by n, as described in the previous slide. Now we just add weights to it to have a specific time quantum for each thread. So this is how we do it. We say, okay, target latency times the weight of this thread divided by the sum of weights in the system. So if in this equation everybody has the same weight, so if let's say WI is 1 for everyone, then this formula becomes exactly like this formula, because it would become 1 times target latency, which is target latency. And then here it would be 1 plus 1 plus 1 n times, so it would become n. So it becomes target latency divided by n, which is exactly like this. But if you have different priorities, so if threads have different weights, then each one of them gets a different time quantum. So, and then if you divide time quantum of thread I by time quantum of thread J, target latency in both of them get canceled. Let me actually do that. So let's say we want this Qj. Well, Qj equals Wj times target latency divided by sum of weights. So this is canceled by this. Target latency is canceled by target latency. And this becomes basically Wi divided by Wj. Right? So now the time quantum that thread I gets is Wi times the time quantum that that thread J gets divided by Wj. So now they're getting proportional time on the CPU based on their weights, which is exactly what we wanted. Okay. So here is an example. We can run that example. I'm going to just move on. Now, we have to do one more thing. As you can see, we're just building on this max-min fairness. We started with vanilla max-min fairness. We then added target latency to have responsiveness. Then we added weights. Now there is one last piece that we have to do. And I think I can explain that with an example. So let's say I have two threads, A and B. And let's assume that thread B's weight is more than thread A. And let's assume that thread B so far has gotten 16 time units on the CPU, and thread A has got 4 time unit on the CPU. Let's say let's just for the sake of argument say that thread B's time quantum is 16 and thread A's time quantum is 4. So initially nobody had anything, then we gave it to B. We gave it to A and then we gave it to B, and now it's what you can see. Except if I run max-min fairness now, I would pick A because A has gotten less than B, and I would give the CPU to A. Should I really do that? The answer is not really. I have to divide this actual CPU time by threads weights to get a normalized time on CPU, which we're going to call virtual runtime. Instead of actual CPU time, I have to now look at virtual CPU time, which is the actual CPU time divided by weights. So if this is the case, that this is like time quantum of thread B and this is time quantum of thread A, you can see that there is a 4 difference, 4 times. So time quantum of thread B is 4 times time quantum of thread A. That means that B's weight is 4 times A's weight. So let's say A's weight is 1, then B's weight is 4. Now I divide this by 4. Sorry, I divide, so let's say A's weight is 4, then B's weight is 16, right? Now I divide A's time by its weight, I get 1. I divide B's time by 16, it gives me 1. So at this point, both of them are the same. Although B got more actual CPU time, but it's okay because B has more weight. Now, if I want to choose now between B and A, I have to break a tie. They're equal. Whereas if I were to just use their actual time, I had to pick A, which would have led to an unfair scheduling. So to summarize, what we did for fairness, for adding weights and priorities, we did two things. First of all, we made time quantum length be thread dependent by basically adding the weights into the equations. We also, the second thing we did, instead of looking at actual time when we do max min, we look at virtual runtime, which is basically the actual time divided by weights. So we multiplied time quantum by weight and divided actual time by weight. So both of these two together now give us weighted max min scheduling. And to make this even more interesting, this is basically what you have right now implemented. This is a simplification, of course, but the essence of what you have in Linux, in completely fair scheduler in Linux, is basically this notion. So it's a it's a weighted max min fairness with dynamic time quanta, which is basically the current scheduler in Linux. Got a question? Does Stride scheduling run the risk for a starvation for low priority tasks if there is a constant stream of high priority tasks? Yes. So any, let me think. So I think it's an unfair comparison what this question is asking, sort of. So let's say that you have a system that high priority tasks come and go, get served, and another one comes, and so there's just a constant stream of high priority tasks coming. In that case, if you are a low priority task, you probably get starved, no matter what the scheduling policy is, usually. The only policy that I could think of that might not starve you is lottery scheduling, because it randomly picks a ticket, so there is a chance that you get the CPU. Now, if, however, so this basically answers that question. Yes, Stride scheduling does the same. So if basically high priority tasks keep coming, new ones, then if you have an old low priority task, it will just start. Now, a better comparison, I think, is fixing the number of tasks in your system. Let's say I have 10 tasks, 9 of them high priority, 1 of them low priority, and then discussing whether or not this low priority gets starved, right? Because for instance, in a strict priority, this low priority gets starved, because all the high priorities, they always run, right? But with the Stride scheduling, this scenario does not lead to a starvation, because the high priority ones get the CPU, but at some point, the low priority will have the minimum pass, and then it gets the CPU eventually. And then it has to wait for all the high priority tasks to catch up. So it doesn't starve the low priority task. But if you know, high priorities keep coming, new ones, then yes, almost every scheduling, but the purely random lottery scheduling could lead to starvation. Okay. I'm going to quickly walk you through how we can compare schedulers. That actually was a good segue to the discussion that I'm going to have now. How do we compare different scheduling policies? We generally speaking have 3 ways of doing that. One is a deterministic model. Let's say you can write down the the exact model of your scheduler mathematically, and then analyze them again mathematically. Let's say if you have deterministic algorithms like stride scheduling, for instance, like factor out the tie-breaking rule, then you could actually deterministically model them for any single workload that you might have. That's one. Now, if you move on to scheduling policies that are more random, then you probably have to start thinking about models that have random variables and distributions and stuff. So that's where the queuing models come in. So queuing models, which we will actually see later on after talking about I/O, actually address this. So they give us a tool to mathematically study random processes and scheduling policies. And the last way of doing this is just to simulate. So don't do any analysis, just implement it in a simulator, and then simulate it for any given workload, and then compare your systems. I got a question. Can you explain weighted max-min fair example again? Like how higher priority tasks are favored? Yes, so if I go back here, let's say okay, let's say I have two tasks. I have A with weight 4, and I have B with weight 16. Now, let's say that the target latency is 1. Or let's say target latency is 6. Let's see. Let's say target latency is 20 milliseconds. So this is target latency. So what is the time quantum for A? Time quantum for A is basically 4 times 20 divided by sum of weights, which is 20. So that becomes 4. And then what is the time quantum for B? So this becomes 16 times 20 divided by 20. Sorry for the handwriting, I'm using the mouse. So this becomes 16. So time quantum for A is 4, time quantum for B is 16. Now let's run max-min fairness. So initially, let's say both of them have got nothing. So both of them have 0. So we need to keep track of virtual time for B and virtual time for A. So which virtual time is basically the actual time divided by weights. Now, initially, both of them have 0, right? Both of them are 0. So we have to do a time breaking rule. Let's do in favor of A. Let's decide that A should get time. It's randomly, let's say we pick A. Now, A gets to run for how long? For 4 seconds or 4 milliseconds, whatever the unit is. So A runs for 4. This is A's time quantum. Now, at the end, what is after this? What is the virtual time of A? Virtual time of A is actual time of A divided by its weight. So the weight is 4, the time is 4. So 4 divided by 4, that's 1. So virtual time of A becomes 1. Now, let's look at B. So now virtual time of B is still 0. Virtual time of A is 1. So we have to pick B. Now we pick B. How long it's going to run? Well, 16. So time quantum of A, time quantum of B is 16. So B now runs for 16. And this is basically answering your question. How is B favored over A? You just saw that B got to run 16 milliseconds, whereas A only ran for 4 milliseconds, right? But then at the end of this process, now what is the virtual time of B? It's going to be 16 divided by 16, which is 1. So now we're back to the equal situation. Now A and B are equal because weight-wise, B's weight is 4 times A's weight. And as you can see, the time that B got on the CPU is 4 times the time that A got. So if you run this algorithm again, you're going to get A again 4 and B again 16. And so on and so forth. So we keep this weight going on as we continue. Hopefully that explained, that answered the question. Okay. So one thing, if you want to compare scheduling policies against each other, you have to consider that when you go with the simulation route, you have to make it equal for all scheduling policies when you want to compare them. Here is an example that is important. Let's say you have 2 policies, policy A and policy B, and you want to compare them. So let's say you're working for this company and they want to see which policy is better. So you go and implement policy A, you implement policy B. Now you want to run a simulation. What you do is, well, you create an infinite loop, and then you just create tasks as you go. At some time, you start measuring the performance metric that you're interested in. You might be interested in throughput. You might be interested in fairness. You might be interested in wait time, response time, whatever the performance metric that you're interested in. So at some point, you start measuring it. And then let's say you continue measuring it for like whatever time, like 1 day, 2 days, and then you stop. And then take the average, and then you say, okay, policy A did this, policy B did this, and policy A's numbers are better than policy B, so A is better. Is that a good approach, what I just described? The answer is no. This is not a good way of comparing A and B. The reason is because let's say A was SGF and B was FCFS. Now, after 2 days of running A and B, are you sure that the tasks that completed under A are the same as the task that completed under B? And the answer is no, not necessarily. Because under A, all the short tasks are gone. Under B, all the tasks that came first are gone. So after 2 days, if I look at the tasks that have finished, I see 2 different sets of tasks. And if I compare the performance for these 2 different sets, it's a biased comparison because one has run the algorithm on bunch of threads and the other one has run it on another set of threads. Now, how do we, make sure that this doesn't happen? One way, one solution for sample bias is to, instead of fixing time, instead of saying, oh, I measure the performance for 2 days, you should measure performance for a set of tasks. If you go back to what I just said when I was comparing 2 policies, somebody asked a question, I said, fix your tasks and then measure whatever you're interested in. You can do the same here. So you can say, okay, I fix 1,000,000 tasks, and then I run FCFS on it, and then I run SGF on it. It could be that SGF takes, under normal circumstances, because both of them are work conserving. If you have a uniprocessor, both of them will take the same amount of time. If the context switching time is equal. If the context switching time is not equal, then it might be different. But let's not get there. Anyways, so you just don't care how long each one of them takes. You just go as long as they run to the last task. Once the last task is over, now you look at your numbers. Now both of the algorithms have been running on the same set of tasks. So now you have an unbiased comparison on your hand, and you can make conclusions instead of the previous version where you have a biased numbers. Okay, finally, this is just a comparison of different things that we've seen. Let's walk through them. So if you remember, FCFS was really good if you cared about throughput. Here I add, because this considers if you have non-zero context switching, because FCFS basically doesn't context switch much. It only context switch once one task is done, and it context switches to the next task. So the number of context switching is minimum compared to all the other ones, like round robin or SGFS or all of the other ones. Not SGFS, SRTFS, shortest remaining time first. So this basically gives you the best throughput in terms of if you have non-zero context switching. Now, if you want to minimize average response time, you can use SRTF. If you care about I/O, as we saw in that example, you still can do SRTF. If fairness is what you care about, what we saw, weighted max-min fairness is the way to go. Now, I think at this point I can compare weighted max-min, the version that we talked about, and stride scheduling. They look alike. They have one simple, actually two differences: stride scheduling and weighted max-min fairness. I think I asked this question last term in one of the quizzes. We might ask again. So although the end result of both of them might be the same. So if you run them for a long time, and then you look at the actual time each task got on the CPU, stride scheduling and weighted max-min fairness give you the same probably numbers. But there are two differences. One, in a stride scheduling, we had a fixed length of time quantum. So the time quantum was the same for everyone. Whereas in weighted max-min fairness, each thread had different time quantum. That's first. The second one is that in weighted max-min fairness, we also considered target latency and responsiveness. So basically, we're even changing, even if everybody had the same weight, with weighted max-min fairness, we're dynamically changing the length of the time quantum, whereas in stride scheduling, the time quantum is fixed. So these are the two differences. But anyways, if you care about fairness, you can either go with weighted max-min fairness or stride scheduling. Both of them give you fairness. If you care about fairness in terms of wait time to get CPU, then round robin is your to go. If you want to favor important threads all the time and you don't care about starvation, then strict priority is what you want to do. If you care about proportional sharing, then you have three options: lottery scheduling, stride scheduling, and max-min fairness. So this is not a complete list. It's just, lists some of them. Don't take it literally as the best and the only choice. So these are just some of the choices that you could make. Okay, so that's pretty much it for uniprocessor scheduling. Now, for the remaining time I have, I'm going to start talking about multi-processor scheduling, which is kind of like a more, you know, modern scheduling topics, if you wish. Still, like a decade at least, 2 decades old topics, but definitely more recent than uniprocessor scheduling. Okay. So what are we going to see in this lecture? I'm going to actually first, before talking about multiprocessor scheduling, which if you look at this list comes at the end, I'm actually going to walk you through some of the challenges that exist in multiprocessors. I really wish that we had more time to define a project. I probably we should have a advanced operating system added to our to the courses that we offer, and there we could like define a lab on multiprocessors, because what you're doing right now, although the boards that we have all are multi-core processors, we're just using one core. Then the moment you add the second core, then you open the door for all sorts of challenges. Some of that we're going to see in this slide, and then addressing those challenges are really interesting topics in operating systems. So I'm going to just touch and scratch the surface with regard to multiprocessors. This is a really interesting topic. And this is basically the connection between operating systems and then distributed systems, because here is where we're going to talk about having multiple cores now, multiple processing units operating on the same chip, whereas in distributed systems you have multiple processing units operating on different servers. Anyway, so I'm going to walk you through some of the background knowledge that you might want to know about the architecture of these multiprocessors. Then we'll see how these different architectures create challenges on what we have seen so far. In particular, we will revisit the synchronization primitives that we saw, and we'll see how we need to think differently in a multiprocessor than we thought in a uniprocessor. And then we start talking about load balancing in multiprocessors, and then some more advanced scheduling policies that target multi-threaded processors, sorry, multi-threaded programs. And that would conclude this lecture. Okay. So let's first start with multiprocessor scheduling. So the simple goal of scheduling a multiprocessor is to basically, if you have an available CPU, let it run an available thread. That's pretty basic and simple, right? If you have a CPU and you have a ready thread, then start running. Why are you wasting time? You will soon see that this is not that easy. This simple invariant and simple goal is basically not that simple. The reason is mainly because of the modern architecture of multiprocessors. In essence, it boils down to high cost of cache coherency protocols and also the non-uniform memory access latencies. I'll talk about both of them in details. Actually, not details. Well, I'm going to scratch the surface. So we'll just see them so that you know what they are. So let's start talking about some of the more modern architectures when it comes to processors. So if you remember, I talked to you at the beginning of the course about Moore's law and how we were making our uniprocessors faster and faster and faster until we hit the power wall. We couldn't do that anymore because we started decimating a lot of power, and then if we were to just continue on the same trajectory, we would have made our processors melt. So energy became something that architects started looking at. Modern processors right now on your CPU, on your tablets, on your cell phones, some laptops maybe, are asymmetric multiprocessors. We have on our processors different processing units with different power, different computing power. The reason we have this is because the power that is consumed by a processor is very much related to the performance of that processor. So if you have a high performance processor, it basically implicitly means that that processor is consuming a lot of power. Now, you have a power budget. If you put if you make all your processors on your chip high performance, then it's going to consume a lot of power, and it's going to make that that device very hot. Now, if you're talking about a cell phone, you cannot put a heat sink on your cell phone to make it cool. If it gets hotter than a certain temperature, then it's going to burn somebody's hand, and it's not just going to work, right? So we can't make all of our processors fast and performance centric. We actually don't need to do that either, because not all applications are performance hungry. We have some applications that only use memory or I/O a lot. So they're not really using a lot of computing power. They're using network a lot. They're using I/O a lot. They're using a lot of memory requests. So we don't all of our applications aren't like doing matrix multiplication and arithmetic, so that they need a lot of computing power. So what architects have come up with is a hybrid model where we have really powerful high performance CPUs on the chip. We also have low power and low performance cores on our chips. And if the application doesn't need a lot of computing power, we can actually run it on the low power, low performance core. And by doing that, we can save power. This, however, creates a lot of challenges, as you might imagine. Now, how do I decide which application has to run on the little core? How do I decide which application have to run on the high performance core? What do I do when one of the cores is not being used? Should I turn it off? Should I put it in a middle state that it doesn't consume a lot of power, but it's not completely off? So all of that. Very recently, we started also adding accelerators like TPUs, for example, or FPGAs on the same board. In particular, the boards that you're actually using, the Intel boards, DE1 SoC boards, they have two ARM processors connected to an FPGA, which is an accelerator, on the same chip. So on the same exact chip, you have an accelerator and bunch of CPU cores. And the accelerator could be used for all sorts of things. If there is a need for, let's say, machine learning application, it needs to train a model. It's going to do a lot of matrix multiplication. You can actually use the accelerator for that. Now, one of the examples that ARM have come up with, and it's very famous. Almost most of your CPUs are are doing this architecture. It's called big little architecture. It basically has what I just described, and you can see here you have really powerful cores next to low power cores connected to your GPU and connected to your accelerator on the same chip. And although this is good for energy consumption and efficiency, it actually creates a lot of challenging questions for the operating system to now manage all this heterogeneous resources. We'll try to address some of this. Basically, I guess I have only one slide on energy aware scheduling at the end of this lecture. Probably we'll talk about it next lecture on Thursday. The other aspect of modern architectures, what time is it? Yeah, I have time. Okay, the other aspect of modern architectures is the creation of systems with non-uniform memory. So back, like not back in time, but like early architectures, when it came to multiprocessors, they would connect all the CPUs to the same memory controller, and then the memory controller was connected to memory banks and memory blocks. So basically, this CPU, if it wanted a data from this memory, or if it wanted a data from this memory, it would take the same time for this CPU to access that memory. It had to send a request to the memory controller. The memory controller will route the request to one of the banks, and then would get the result back and send it to the CPU. So no matter where you want to access, it would take the same amount of time. And that is basically uniform memory access, UMA. These days, however, the modern architecture for multiprocessors is not that way. Usually what you see is something like this architecture. In this architecture, you have each CPU connected to its local memory bank or local memory block, and then different CPUs being connected to each other. Now, if this CPU1 wants to read a memory block that is here in this bank, then it would just talk to this memory controller and get the result back. It would be a local access. That's what we call it. However, if CPU1 wants to read a memory block from this memory bank, it has to go through this network on chip to connect to talk to CPU2 to the memory controller connected to this, get the result back, and then the result is routed to CPU1. And that is a remote access, and that takes more time than accessing your local access. And that's pretty much what the name suggests, non-uniform memory access. So now this is again an artifact of the way that the CPU, the processor is architected. So basically, in this model, if you have a load instruction, you don't really care about where the data is. You sort of know on average how long it takes. In this model, if you have a load instruction, you actually care about the address. If the address is somewhere here, that instruction is going to be fast. If the address is somewhere here or here, that instruction is going to be really slow because it's going to go through the interconnect between the CPUs. So that's another thing that we will see how it would introduce more challenges than what we saw in uniprocessors. So I'm just going through the different architectures that we see in modern CPUs. You will see how we can address each one of them later on in this lecture. So first, I'm going to just list them so that you know. The last one that I'm going to talk about is basically the cache hierarchy in multiprocessors. So this is a typical multiprocessor architecture. You have your CPUs, bunch of them, right? Each one of them has its own private caches, L1 and L2. These are private, meaning that only CPU 1 can have access to these caches. And only CPU 1 can access to these caches, only CPU 2 can access to these caches, and only CPU 3 can access these caches. But then all of them share this L3 cache. This is a shared cache. So all of them are through an interconnect connected to this shared cache. And then from here, they go to this memory controller and beyond. So from this is the shared last level cache, and then here they go to access the memory. So here is another picture of this. As you can see here, I have the CPUs listed here, right? Here you can see the last level cache. So this whole bank in the middle is the last level cache. It's shared between the CPUs. All the CPUs have access. So there is a ring, as you can see, that connects all of them. So you still have some sort of NUMA kind of effect. So if this CPU wants to access some slice of last level cache that is here, it's going to be fast. But if it is here, it's going to go through this interconnect and then come back to it, which might be a little bit. So it's actually different, right? It's not the NUMA that we saw. NUMA was about memory, but it's a very similar concept on last level cache. But these are last level caches. Each one of these CPUs has its own cache that you cannot see in this picture. So it's a private cache for them. And then here you see the memory controller, and then from here you're connected to the DDR channels, and then you go to the memory. Now, why did I even talk about this? Why cache hierarchy is important. So here's one scenario that we're going to see how having different levels of caches and then having private and shared caches could be problematic. So let's say that thread A modifies the data inside the critical section. So let's say thread A and thread B, there is a race condition between them. So there's a critical section. We have protected that critical section with locks. So both of A and B need that piece of data. Now let's say A is now running inside critical section, and it modifies the data inside its critical section, and then it unlocks the mutex. Now next, B gets the lock, so it locks the mutex, and then B just reads that data. Pretty benign in what we see in uniprocessor. This is basically what we have talked so far, right? That's pretty okay in uniprocessor. There is nothing to be seen here. Well, everything should work. You have critical section that is protected by mutexes, by a mutex, and then A modifies it, and now B reads it. As long as you are holding locks and stuff, it should work. No problem, right? Yes. But what if thread A, so this is easy if you have only main memory, no caches, or if both of the threads are running on the same CPU with the same caches. But what if thread A is running on one CPU and thread B is running on another CPU? And what if each one of these CPUs has its own private cache where you can cache the data? What happens? Let's look at it. Let's consider this example. I have CPU A and I have CPU B. For simplicity, I'm assuming that each CPU has its own one level private cache. So just level 1, L1 private cache, each one of them. And then there is an interconnect, and then there is the memory. So let's see what happens. Let's say this is the shared data that we were talking about. So let's say initially CPU B loads this address to read it. So let's say CPU B first acquires the lock, reads that, and it's done. Then it unlocks the mutex. And then let's say CPU thread A this time acquires the lock, reads the data. So every time you read the data is brought to your cache, right? That's what you can see here. Because as we talked about, this cache is there to make things faster. So you want to cache things that you recently have seen because you might see them again. So now I have one copy of this data in both of the caches. Now let's say thread A wants to modify this. So let's say thread A does an executes an add instruction, adds this data to R4 and stores it in R1. And then let's say it stores R1 to X. So what happens usually is this part depends on how the writes are being done. But at this point, let's assume that the write is only being written to my private cache because that's where the data is. So I just write it to my cache. So now this data has been changed. And now I'm done. Thread A is done. It releases the mutex. Now, what happens if thread B again acquires the lock and wants to read the data? Well, not gonna see this. B is not gonna see this because this is private cache. It actually thinks that, oh, I have the data in my cache. So it may probably go into the cache and say, oh, I have it here. And then it reads the old data that was stored in this cache without even noticing that the data has actually been changed by thread A. And that's pretty much cache coherence problem that we want to see how we can address. So just introducing these private caches, as you saw, creates this problem that now the same shared data, we have different copies of it on different processors' caches. We wouldn't have this problem if we didn't have any cache, right? Or if we were running this on a uniprocessor. So if this didn't exist, then CPU A would have just written the data back to the memory. So this would have become the new data, and then thread B would have read the correct data. This problem is a product of having this local caches, and each one of the threads reading from these caches instead of reading it from memory, or writing to their caches instead of writing into the memory. So hopefully the problem is well defined, that what is the problem that we're trying to deal with. I guess I have, how many minutes do I have left? I have 10 minutes, okay. Now, let's see what we can do about this. So the one thing that you can do, and is pretty much done in modern multiprocessors, is to put in place a cache coherence protocol. So the job of this protocol is to make sure that you don't have the situation that we just saw. It makes sure that everybody has the copy in their caches that is reliable, that is up to date. And if your copy is not up to date, you have to either disregard it, just throw it away, or you have to update it. So that's what the cache coherence protocol is going to do for us. Okay. So how do we approach this? How do we solve this problem? How do we design cache coherence protocols? There are two goals that we have to have, or two invariants we have to have for any cache coherence protocol. The first one is the single writer, multiple reader invariant, which says at any given time, you either should have a single writer or multiple readers. You cannot have both of them at the same time. You cannot have multiple writers. You cannot have one reader and one writer and multiple readers. You only can have either one writer or multiple reader. So this is the first thing that you have to have. You have to implement in your cache coherence protocol. So basically, one writer means that only one CPU has the read-write access to the data. You cannot have multiple CPUs having the same access to the data, having the same read-write access. Or so either this happens, or nobody has read-write access, and 0 or more reader exist. So 0 or more CPUs have read-only access. So this, you should be at any given time in either of these two situations. You cannot be in both of them, and you cannot be in any other situation. So you have to be either one writer or 0 or more readers. So this is the first thing you have to do. The second thing, which is kind of more technical to implement any cache coherence protocol, because there are so many different cache coherence protocols out there. It says that the value, so if you want to implement any cache protocol, you have to divide your time logically into intervals, and then you switch between these intervals as the accesses change. So as these accesses change between CPUs, you are going to draw lines between intervals. And when you do that, you want to make sure that the value of the shared data at the beginning of each interval is equal to the value of this shared data at the end of the most recent read-write interval. Basically, if I were to translate this to you in plain English, it means that any reads that is going to happen later on after a write should see the value of that write. So if you have if you have an interval where somebody has a read-write access, at the end of that interval, the value of the data should be propagated to everybody else who is going to come next and read this data, which is basically what we saw in the example. A changed the data, and the data was not propagated to B, and B started reading something false and wrong and outdated. So this invariant says that you have to prevent those situations. So here is an example. Let's say this is time. Let's say initially I have CPU A and B in read-only access. So the entire time, no matter how long it takes, that A and B have read-only access, it's going to be one time interval. And let's say the value of the shared data is 2 at that point. Let's say at some point C wants to write. So C gets read-write access. So we're going to invalidate this access for A and B. Now A and B don't have any access. C has access, read-write. And let's say C is going to change this 2 to 7 sometime in this interval. We don't know where. It could happen here, it could happen here, it could happen here, sometime, right? Let's say after a while, so no matter how long it takes, it's going to be one interval where C has read-write. Then A and B again want to read. So we're going to have A, B, and C, all of them in read-only. Now, if you see this, the value that this A, B, and C should see has to be the value at the end of this read-write interval. So at the end of this, the value has changed to 7, and this is the value that A, B, and C have to see in this interval. Now, one thing that I have to point out in this is that I'm just showing you this time interval for one memory address. right? That we're looking at its value. So we're going to have these for every single memory address, because that's what we care about, right? We want for any memory address to implement this cache coherence protocol to make sure that that memory access, that memory appears in everybody's caches correctly, and you don't have outdated copies of that memory in somebody's caches. So cache coherence protocols are going to implement cache coherency for every single address, memory address, right? That's basically the basic of it. Now, to get a little bit more technical, how much time do I have? I have 4 minutes. So I think I can finish this slide. So here is what you usually see in cache coherence protocols. So this is a superset. As I said, there are so many different cache coherence protocols. We're going to see one of them, for example, one or two. So generally speaking, different cache coherence protocols, they define states for each memory location. So for each memory location in each CPU, actually, right? Each CPU has a state with regard to each location. So it's a mapping from CPUs to memories, and then this mapping has a state. It's either valid or invalid, so that's validity of that. If this CPU has a valid state for this memory location, it means this is a valid valid access. It could be dirty or clean. We'll see exactly what this means. So it could be dirty or clean. So if the state for this CPU for this address is dirty, it means that this CPU has written to this address. If it is clean, it means that it hasn't written in that address. Exclusivity, it could be exclusive or non-exclusive. If this CPU has exclusive access to this address, it means that only this CPU can have access to this, and everybody else doesn't have any access. And if it is non-exclusive, it means that others could have access to this CPU, to this memory location. You have ownership. So a location could be owned by a CPU or could be owned by others. So either a CPU owns a location or it doesn't. And then you have permission. So it could be read-only or read or write, as you saw. So if a CPU has a read-only access to a location, it can only read from that location. If it has read and write, then it can read and write to that location. So these are the states for a pair of CPU and memory location. Now, in essence, this boils down to defining 5 common states, again, for each CPU and each location. For a pair of CPU location, we define modified, owned, exclusive, shared, and invalid. And if I put them in a chart, I'm going to actually explain what you see here. So I have owned, modified, exclusive, shared, and invalid. So if a CPU for a memory location is in any of these states, O, M, E, or S, that means that it's a valid situation. And other than that, it's invalid. So if your CPU owns a memory location or has that memory location in a modified state or exclusive state or shared state, it means that your CPU can access that state, and that access would be a valid access. Anything other than that, it would be an invalid. So we're going to say this access is invalid. This memory location for this CPU is invalid. You cannot use that memory location. Then you have ownership. So if a CPU has a memory location in O, M, or E, all of them mean ownership. You have the ownership. Note that exclusivity, ownership doesn't always imply exclusivity. So you could own a memory location, but it might not be exclusively for you. You can own it, but then share it with others. If you have a memory location in owned or modified state, it might mean that you have it could be dirty, right? So either modified or ownership, it means dirty, dirtiness of that memory location. So I think that's yeah. And then if you have it in E or M, that says that you have it with exclusivity. So it's exclusively for you if you have it in E or modified. Because if you're modifying a memory location, because of that, the first invariant, which was single writer, 0 or more readers, if you're modifying, you're that single writer. So you exclusively have access to this and nobody else has. You can get that exclusivity with just a state E. Okay, so this is basically just describing different states and what they mean. Now, not all different cache coherence protocol use all of these states. So they usually use subset of these states to implement those two invariants. So the end goal is to implement those two invariants. And there are different ways of doing that. So we're going to see two different cache coherence protocol that use different set of these to implement those. And I'm pretty sure that I'm over time, so I'll talk about those in the next lecture. Thank you so much for those of you who have attended the lecture, and those of you who are going to watch this later on. Please take care, be safe, stay healthy, and talk to you on Thursday. Bye-bye.